Here's a 3-methyl-1-butene, and we have this special reagent you want to become familiar with, mercury 2 acetate. Here's acetate, has a negative charge. Here's mercury plus 2 charge, and so here's 2 acetates with there. And it's all done in the same pot, but it's done in 2 reactions. So just this reagent is added, and you let it do its thing, and then you're going to add that reagent. So when we get into more organic synthesis, we might have 1 through 6 here, things that are done. So under the reaction conditions, this gets heated up a little bit, and an acetate pulls off, leaving a positive charge here. The double bonds grab this, and I'm going to go ahead and put the acetate back in there. You could leave it out, doesn't really matter. And this is called the mercurium ion. Has a IUM ending, meaning positive, and it's a 3-membered ring. It holds everything together, and we don't have a carbocation. Positive charges on mercury. Normally, a lot of our addition reactions to an alkene, we get this carbocation, and what are carbocations known to do? Besides eliminate hydrogen and form an alkene. Yeah, they rearrange. So notice this kind of locked in place, and then water comes and hits there, and in the presence of water, this hydrogen come off, and put the OH there, and then next up, this is a reducing agent, and so now I'm going to just draw that N carbon like this, that carbon there, this, and this looks like regular old hydration of a double bond, and it looks like what type of regioselectivity? Markovnikov. Now let's just compare this to our straight up, if we just had acid catalyzed hydration, our first hydrogen would go on there, and then right here, you might have something that looks like this, and there we have this hydride shift, leading to a more stable carbocation, and then ultimately, there's our rearrangement. So the whole reason chemists came up with this reagent and reaction is it stops carbocation rearrangement, because this gets locked down. Carbocation can't rearrange, and so our end product, we just draw to make this look like this thing up, so we can compare it. You know, if before you learned about carbocation rearrangements, you'd say, oh, Markovnikov, the hydrogen goes there, the OH is going to go there. Well, it doesn't, because it rearranges, and then eventually you get your alcohol, tertiary alcohol. We really wanted this secondary alcohol. So this is the reagent that can do this for us. Stop rearrangements. So here's about where we ended last time. And once again, we don't get our OH here. We do put the first hydrogen here, and then there's a methyl shift, and we get our OH down there. So chemists said, what if we want Markovnikov Regioselectivity? And so this thing is called Oxymercuration, Demercuration reaction. Here's our mercury 2 acetate, and here we're in water, and here's this intermediate. We get an OH on the carbon bearing the lesser amount of hydrogens. The carbon that had the greater amount of hydrogens gets the mercury, and then eventually we get our Markovnikov orientation. So it's milder conditions than direct hydration, and a little cleaner reaction. We don't get any rearrangements or something we haven't talked about, polymerizations. The reagent is mercury 2 acetate, which under reaction conditions dissociates, and we get this electrophile. And then the electrons in the pi bond and the electrophile attack each other. Of course, I'd like to say the pi bond attacks the electrophile, so you draw your curved arrows in the correct direction. The 3-membered ring is called the mercurium ion, and what is important is that it follows Markovnikov's rule. So here's a nice Lewis structure of the reagent. Mercury's big and has a bunch of d orbitals, it's very polarizable, so a little heat and this thing readily disassociates. And then here is business end of the electrophile. Electrons in the double bond, grab that thing. Some electrons, mercury, grab this thing, and here is our merconium ion. And I should draw it on the whiteboard this way. And then water hits, and we have this oxygen with a positive charge and 3 bonds. Weak base can pull that off. And here is an organomercurial alcohol. And I said at the beginning on the whiteboard that the water has a choice between those 2 carbon atoms. And it's going to choose the more substituted carbon to form the Markovnikov product. And the reason is a lower transition state. But here is something maybe a little new, anti-addition. What that means is the OH is down below and this thing's up above. And then we add the reducing agent, which strips the mercury off. And when you do this in a glass flask, it mirrors the flask. It's a beautiful thing to perform. Of course, it's toxic with all this mercury. So a hydride furnished by the sodium borohydride replaces the mercury, and here is an alcohol. So this is what we get when we run the reaction in water. We can just as easily run the reaction in an alcohol, and then we end up forming an ether. So here's an alkene, and here's our Oxymercuration, Demercuration reagents. What are we going to form? And let me just put an aqueous here. Just saw in the PowerPoint, if we did an alcohol, we'd get an ether. We're going to get an alcohol. Can we just straight up name the alcohol? So if it's Markovnikov, hydrogen's going to go here, the OH is going to go there. But raise your hand if stereochemistry is your favorite topic. I got to work harder. I got to work smarter. I'm going to go ahead and add this hydrogen here, and I'm going to add it in black. And I'm gonna just go ahead and put the CH there. I'm going to put the original hydrogen there. I'm going to put the new hydrogen there, and the OH there. So now the question is, why did I do that? I did that so you could learn the stereochemistry of it. We already know that it's Markovnikov Regioselectivity, and that the rich are going to get richer, and the OH is going to go there. This thing had 1 hydrogen, this thing has no hydrogen, this thing's going to get 2. But now if I work real hard and try and draw the intermediate, I'm going to have to draw something that looks like this. Got warmed up, look at that one slide. This water wants to hit the more substitute. So there's kind of a hydrogen sticking out here. I'm going to put it up there. This comes this way, and then when we add the sodium borohydride, we're going to get this product here. So these are on opposite sides of the ring. That is the anti-addition nature. Alright, any questions? Anti-addition product. Now our first example, same reagents. We might draw it like that and say it's anti-addition, but the sigma bond rotates and one really can't tell. Rotates all day long. Can't see the anti-addition product. But that anti-addition product occurs due to the way that ring holds things in place, and the water approaches the opposite side of the mercury. So let's adjourn for today.